Hello and welcome to this video on solving radical equations. Before we get into the steps of doing it, we want to talk about some vocabulary and some general ideas about this topic. Generally speaking, a radical equation is any equation that has a variable underneath a radical symbol, or the variable would be in the radicand portion, or a variable with a rational exponent that would match the radical you are looking for or talking about. As far as those parts of a radical vocab words I mentioned, the actual square root looking thing is actually called the radical symbol. The part underneath of it is called the radicand. And then the index we're going to be working with today is going to be a 2, even though the 2 is not going to be there since that's kind of the default of a radical. And then, so it's not going to be showing up. As you can see on the right side, this is a square root right here. And that is the same thing as x to the power of 1/2 as a rational exponent version. But we won't be seeing rational exponent equations in this particular video. Keep in mind that a radical equation with a variable under the radical is different than just having a radical in the equation in general. On the left-hand side, you can see that x is underneath of the radical symbol, and that makes it a radical equation. On the right-hand side, we have a square root of 2 in the equation, but that doesn't make it a radical equation itself. The general steps of solving a radical equation is by undoing our square roots by squaring them. This is because square roots and squares are inverse or opposite operations. The most common example of this people know is addition and subtraction are opposites, and then you have multiplication and division are opposites, and there are more opposites further on in math, and it is a very important idea of opposites in general. The steps that you'd be doing to solve radical equations are generally the same no matter what equation you're doing. You want to first isolate the radical symbol. So basically, the radical and everything underneath it would be on one side, and then everything else in your equation would be moved using algebra to the other side of the equation. Once this has happened, you want to be squaring both sides. And this is something you want to be careful with because there's a lot of opportunity for a common error to happen. If you look over to the right side of the slide, we have a correct version and an incorrect version of squaring both sides. And this is especially difficult when you have more than one thing. On the left-hand side, we see 2 plus 4 equals 6. If I wanted to square both sides of this equation, I would square the quantity of 2 plus 4, so I would have to add them together to make 6, and then square it to make 36. That would mean that I have a true equation at the end. 36 is equal to 36. Alternatively, if I saw that same equation and started with the same 2 plus 4 equals 6, and I just squared each of the parts separately, well, that would end up being 4 plus 16 equals 20, but that's not the same thing as 36, and that would be an error that happened there. After squaring both sides, you're just going to use standard algebra to solve what most likely is going to be either a linear equation left over or a quadratic equation left over using methods you've learned in the past. And then you want to make sure to check your answers in the original equation because we're going to be talking about what extraneous answers are soon, and that is a very big possibility of having answers that may not work in these equations. Now that we want to define what an extraneous solution is. So when you're doing these algebra steps, it's possible that along the way you could be creating solutions that you think might work that didn't previously exist in the equation. So these extra answers, or extraneous solutions, are ones you want to check and make sure work, but sometimes they will not actually work for x in the original equation you start with. So when we talk about a square root of a number, we are generally talking about what is known as a principal root. That is, if you put a square root of 4 in your calculator, you're going to get the answer to be 2. Now we know that 2 times 2 is 4, but negative 2 times negative 2 is also 4. So we want to only consider the positive roots. If we want to talk about a negative root, we would have to say the negative square root of 4 would be negative 2. And that is because, well, that's the principal root that our calculator is going to give us. We also don't want a square root function to be able to give us 2 different outputs from one thing, because that would make it not a function at all anymore. And that is something I referenced in a previous video on graphing square root functions themselves. So we want to look at some common mistakes here. So if you look at the left-hand side of the bottom, we know that -3 doesn't equal 3. Well, if we then squared both of those sides, so -3 times itself is 9, 3 times itself is also 9, and then we get something that should be true at the bottom, 9 equaling 9. But we know from the beginning that we kind of don't have something that's true. We have -3 equaling 3. That's the same thing as what's happening on the right-hand side. When we have a square root of x equaling -3, if we square both sides, we're basically squaring a square root, so that should go away and make x, and then -3 squared equals 9. So we found out that x equaled 9. But we start out with something that's not true because our square root is equaling a negative, even though our square roots are supposed to equal their principal roots and equal a positive number. So whenever you see a square root equaling just a negative number, you can pretty much say right away that that's not going to have any real solutions. The x equals 9 in this case is going to be the extraneous solution I mentioned at the top of this slide. So we're going to be talking about how to solve an equation like this algebraically a little bit later on. But if you were to follow those steps, you would find that there are two answers for x. Now, one of those two answers is going to be 7, because if we were to graph our square root part, our basic as a one equation, so it would basically be y equals the square root of -2x plus 30, and you'd graph that part kind of as a separate thing. And then you would graph x minus 3 equals y as its own separate thing. And you basically would have the x minus 3 line, this green line at the bottom, and then you have your red square root function. And you can see right here that they are intersecting at x equals 7. So that's only one answer to make this equation true, because the line is going to keep going in this direction, square root function is going to keep going that direction, so it's impossible for them to intersect more than once. But if you were to solve this algebraically, we'd be squaring both sides and getting two answers. So one of those two answers that I mentioned here is going to be an extraneous answer in this particular problem that we're looking at here. And that's something we're going to explore a little more with graphing and then get into the algebraic steps coming up next. We're now going to take a further look at the difference between the original equations and whether they intersect or not, and finding solutions compared to when you've squared them, and see what the result is going to be. So in our first two rows on Desmos here, we see y equals the square root of x and then y equals -3. This is kind of similar to what we saw earlier. We have the square root of x being equal to -3. And that's our equation that we'd be solving. And as you can see on our graph here, we don't have any intersection points at all. So no solutions to this equation. But if we were to square both sides, and that would kind of look something like this, well, then we would get the result that we have in these two rows, x and 9. So we would have x being equal to 9. So if you wanted to kind of graph those two parts and see where they intersect, we could see that y equals x and y equals 9 are going to intersect right up here at 9. So that, in theory, should be the answer, but it doesn't work in our original equation. The square root of 9 does not equal -3 because we're looking for the principal root here. And so by squaring both sides, we've essentially created an answer that didn't exist before. We don't have x equals 9 as an intersection point for this original equation. At x equals 9, we can see our equations are in very different places. So now looking at a second example, we have another equation that is down here at the bottom. Our square root of x is going to be equal to 2x minus 15. So the equation we're trying to solve, square root of x, would be equal to 2x minus 15. Now, if I were to solve this algebraically, I would be squaring both sides, as we kind of talked about in our steps earlier, and being careful to square both terms in a parentheses there. And so once you've done that, you get that the left side of your equation ends up being just x, y equals x. And we have the other side, if you do 2x minus 15 times itself, that would multiply out to 4x squared minus 60x equal plus 225. And so if we want to see where they intersect, our original equations, they only intersect at x equals 9. So x equals 9 would be the solution to this problem. And we can check that answer by doing 2 times 9 is 18, minus 15 equals 3. The square root of 9 also equals 3, so that x equals 9 works. But say we looked at the squared version, so looking at these two examples, well, now I have an intersection point here and here. So x equals 9 and x equals 6.25. So this 6.25 answer right here would be an extraneous solution. It did not appear in our original equation as intersection points. And so our only real solution of this equation would be x equals 9, and 6.25 would be an extraneous solution. And that covers all the notes and practice you might need to begin trying some radical equations.